So yes, officially then, happy Tuesday, happy garbage day. Welcome back. Thanks for being here, Zoomers and Roomers alike. I have, let's see, example 3 open, which we were working through last time. I also have lecture 4 open. I spent most of yesterday trying to finish the examples to go with lecture 4, but they're not quite done. I'm optimistic that will be up tomorrow so that we can probably start some of that on Thursday and then get into that next week. As we were just discussing, for those of you who are listening to the class through YouTube, project outlines are due on Monday. If you're not sure what you're doing yet and you want to run an idea by me, that is fine. You are allowed to work individually or in pairs. So I just need to know basically what your plan is so that I can weigh in on it. And I will give more specific instructions in a rubric to follow after I get a sense of what people's projects are going to be. It is not a final project, it is an April project. So keep that in mind with respect to the timing of all of these things. Let's see. So we were talking about longitudinal models of factors last time. Does that sound about right? I know it was 5 days ago. I barely know what I did yesterday, so I don't expect everyone to have perfect recollection of this. But just to jog your memory, we were going through an example of measuring a latent factor with 3 observed outcomes. So this is a latent factor of cognition, and these are actually test scores that are going into this as indicators. So this is like a confirmatory factor analysis type of model. And before we can examine change over time in a latent factor, we have to establish that it is in fact the same conceptual latent factor at each occasion. Otherwise, it doesn't make much sense. So in this example, I was able to do that. I was able to get through all of the steps of invariance, loosen a few things up, but most of it was invariant, and then fit the growth model. As a foreshadowing, if you try this and it falls apart, like if you don't get any kind of invariance, or there's so many things that you have to release that you're not comfortable saying it's the same factor, there is an alternative. So this model that we're going to end up with, scroll ahead, foreshadowing. Several diagrams later, the model we are going to end up with, almost, there we are, this thing. This is what's known as a curve of factors model, because you're fitting a growth curve to latent factors. So squiggle 2 here is going to be an intercept factor. Or squiggle 2 is the name of the Greek letter, by the way. I know it's labeled 1, but I call this one squiggle 2 because it has 2 curly cues on top as opposed to squiggle 1 that only has 1. So this is an intercept and this is a slope. But what the intercepts and slopes are operating on directly are latent factors. So this is curve of factors. Formative assessment 2 today. Yes, thank you. I knew I was forgetting something. We'll do that one first. But I'll finish my sentence here. Thank you for the reminder. The alternative to this is something called factor of curves, and those are not synonyms. Curve of factors or factor of curves. I will show you a factor of curves as long as we don't run out of time, because I know at least some of you are going to need this in your lives. A factor of curves is a multivariate growth model where each separate indicator would get a growth model on it. So you'd have like 4 growth curves happening simultaneously, or 3 in this case. And then you fit common factors who are responsible for predicting the covariance among the intercepts and the covariance among the slopes. So it's a different like ordering to what the higher order factors are doing. That's the alternative if you're in a situation where you don't have configural invariance to fall back on. So there are alternatives, but if this process does fall apart. But thank you for reminding me. I knew I was forgetting something and I didn't know what it was. Let me get the icon out so we can talk about formative assessment before we go back into this. And I made notes this morning as I was reading through everyone's answers, because some of you thought of things that I didn't even think of. So that's always helpful. All right. Here we go. Quizzes. Number 2. Okay, thank you. So before we dive back into invariance, we'll talk a little more generally here. So first and second question, advantages and disadvantages of estimating longitudinal models using software for structural equation models instead of multi-level models. And I'm phrasing it this way on purpose because it really can be the same model either way. It's just how you interact with the software to estimate parameters and what your choices are. So you can think of this as like shopping. You know, if you have errands to run, you might decide that you want to go to like Super Target for groceries versus Hy-Vee versus Trader Joe's or something. And the items on your list dictate which of those stores would be most useful. It's the same kind of thing. It's like, well, I need a model that does X, Y, and Z. What is the most flexible approach that will do all the things that I want? And so I want you to have sort of a sense of what's possible. But a lot of the limitations boil down to software specific, oh, well, M+ won't do this or R won't do this, which is why it's good to eventually learn things like Stan or JAGS or other sorts of build your own estimator types of routines, because then you can put in whatever you need and have a lot more flexibility even beyond these two sorts of prepackaged options. So advantages of using SEM software instead of MLM software. What extra things can you do? What'd you write down?
I have one.
You got one.
We can model change over time using latent variables. So we do not have to partition our observed variables into different levels.
Mm-hmm.
The model can do that.
Yes, so that is in the context of predictors. Is that what you're thinking
Yes.
of?
Yeah.
Okay, so yes, the idea is that when we get into time-varying predictors, the idea of representing their between-person variance and their within-person variance separately, we can let the model do that using latent variables instead, which is better for a number of reasons if we have enough sample size. Yes, that's one. Yes?
You can estimate missing predictors. So you can have missing predictors.
Yep, you can bring missing predictors that have missing values into the likelihood. Essentially what you would be doing is turning them into an outcome, but fitting an empty model to predict them. So then all you have is an intercept and some kind of variance. And because there's nothing predicting it, the intercept would actually be its mean and the residual variance would be its variance. But yes, under assumptions though, right?
Yeah.
Normal distributional assumptions and missing data, missing at random, the magical thing. If reviewer 2 wants you to test your missing at random, can you do that? You cannot. And that's why they like asking. Because they know you can't do anything about it but argue conceptually as to why it's reasonable. Yes, those are two good ones. What else? I've got my list here that I made out of your answers. There's enough that literally I think every single person could say something different.
We can use the variance components of our time-varying predictors as predictors of something else.
Yes, random effects can be predictors. So if you want your intercept and your slope to be the x conceptually to predict some other thing, you can do that. In multi-level models, the random effects are only outcomes. All of these things, by the way, are, I think you can say more simply, the advantage is that SEM is multivariate and MLM is univariate. So multivariate, the idea that you can predict multiple columns at the same time is what is going to afford all of these things. What else?
Modeling changes in latent variables over time.
Yes, like the thing I tried to start doing because I forgot you all had a quiz today, even though I read it this morning. So I remembered sort of. Yeah, you can model change in a latent variable as opposed to an observed variable. Why would that be useful? Sub-question. What do you think? Mubarak, why would that be useful?
When you have measuring latent constructs, so instead of using some stuff,
Mhm.
it would be useful to use the actual measurements method.
Yeah, so we can use, rather than using some scores and pretending that they're perfectly reliable, we can use latent variables and try to get a better representation of the construct. Yes. What if you change measurements over time? Is that allowed? In SEM it is. If you're going to add shit up, it's not allowed. But if you're going to use latent variables, then it's okay.
Handle heterotypic continuity.
Heterotypic continuity. Well, that's a new vocabulary word. What is that?
Is where you have a construct that is this, so it's the same thing over time, but it looks different, but it has like the same underlying.
Okay.
I'm looking at you because I know you know this too.
Heterotypic.
So like when
Okay.
we talk about like anger
Uh-huh.
over time and like biting in little kids,
Mm-hmm.
which is the example that I use too whenever I talk about this, is
Yes.
like we know that like in littles, like anger looks different than in bigger kids, but it's still anger. So like when we're looking at anger proneness in like developmental research, like we have different paradigms that we use across time
Mm-hmm.
to account for the same thing. So it's heterotypic continuity because it looks different, but it's the same thing.
Okay. Yeah, we would call that like some sort of vertical scaling or vertical linking, I think, in an academic context. The idea that you're still trying to measure math or, comprehension, but you do so with different instruments that are developmentally appropriate to their level of ability at that time. Cool. Well, that's a new word I can use to sound smart. Heterotypic continuity.
It does make you feel very smart to say it.
Yeah, I like that one. Yeah, so latent variables have advantages for solving problems of measurement over time. Let's see, do we have everything on the list yet? There's actually 2 more that people wrote about that I wrote down that I don't yet have on here. Who else wants to participate? I think everyone in the room has said something at this point. No, T, did you say something?
But I don't have anything else that we haven't already said.
Yeah, okay, fair enough. Zoomers, what am I missing? Several of you wrote down latent basis as an option for modeling nonlinear change that's not in an MLM framework as easily. You can trick it out in MSIM or SIM to have a latent basis. We're going to have one of those in example 3 here when we get to the growth modeling section of that. Another one folks wrote down, easy assessment of absolute fit. So you get your chi-square test of whether your model is not worse than the perfect model. You get your CFIs and your TLIs and your RMSEAs and your SRMRs and all the letters that go with all of those things. Under what condition, though? Balance time. So in SEM, we always have balanced designs in terms of items, right? Like you take item 1, you take item 2, you take item 3. Maybe you don't answer 3, but there's the set of possibilities is fixed. In longitudinal data, when it's in wide format, your occasions are boxes. So you can have time 1 box, time 2 box, but if people don't come at the same times, and you have to use t-scores, which is the way to tell it to use individually varying factor loadings, then there's no absolute fit. It's not possible because there's not a single covariance matrix that everyone shares that to be the answer key at that point. That idea could be exploited for evil instead of good. If you wanted to use t-scores, oh, sorry, I don't know if my model fits, I can't tell. Like if you don't want to check your model for fit, if you have unbalanced time, you can't in the same way. I have a side note about that though. The CFI and TLI and any other fit statistics that are based on the null model and growth modeling need to be different. Because the null model in SEM is the worst possible model, still lets every indicator have a separate mean and variance, it just takes the covariances away. In growth modeling, though, we don't want to give each indicator its own mean and variance. We want the random effects and the fixed effects to do that. So we actually need a nuller model to start from in that case. We need 1 mean, 1 variance, and no covariance, like an empty model would be the null model for each of the outcomes. So you would have to compute your own CFI, like your own null model chi-square, and then recompute the CFI that way. I have a spreadsheet that does that if anybody's in that situation. I'm sure people have wrote an R package to fix it or other sorts of things too. I'm sure that's something that people have already programmed. Okay. Anything else that I'm forgetting? Advantages?
In single SEM. Longitudinal invariance in single SEM.
The ability to test it,
Yes,
you mean?
yes,
Yeah.
exactly.
yes, you can actually determine to what extent you have at least the measures that are in common. Like if you don't have a set of measures that runs through the whole thing, then you could only test it in pieces. But yeah, in theory you could. Yep. What about disadvantages then? Number 2. That segues into the big one, unbalanced time. That's trickier to model in an SEM framework. What else?
You can only use maximum likelihood. You can only use maximum likelihood estimation.
Yes, regular flavor maximum likelihood is the only thing. There's no residual maximum likelihood, and there's no denominator degrees of freedom. So for smaller samples, it's less than ideal. But as several of you pointed out, like if you're going to do SEM, we're sort of assuming you have a big enough sample to do SEM in the first place. But that's not necessarily true if you're only doing growth modeling, because it's difficult to get people to come back over time. You have to probably have fewer people in order to pull that off. Another one, it can be easy to smush level 1 and level 2 together in single level SEM. Yeah, it really is, because it's if you're not thinking about levels of analysis, then it is difficult to make sure that your boxes are covered, because there's no distinction between time invariant and time varying with respect to how the model is formulated. That is a disadvantage. Let's see, what else did we write down? I had some that I thought of in addition to that. Any others that you wrote down?
Single SEM has problems with unbalanced data.
Yes, unbalanced time is, yep. That was the first one that I had listed as a segue from the idea of T-scores. Yes, unbalanced time is harder. Yeah, so like if you have a longitudinal study of kids from different cities, for instance, it's very difficult to try to fit that into a single level SEM framework. You can fit it into a multi-level SEM to some extent, but the traditional wide framework will not work very well for that. Other things, there's not as many choices in the generalized sphere. So if you have trying to predict outcomes that are not normal, there's some other kind, there are fewer choices built into SEM software than there are like univariate multi-level softwares. Some of you mentioned about difficulty modeling nonlinearity in multi-level modeling or SEM. I wanted to add a vocabulary word to your list. There are models, they're called generalized additive models, I believe, that are sort of in the MLM family. And what they do is, it's like an extreme piecewise approach where they figure out what the knots should be and what the function should look like. So it's a way of representing nonlinearity in an empirical way. I read a book about it once and tried to learn a little bit about it, but I didn't get very far. But I just wanted to point that out there. That's like, there are nonlinear data estimated kinds of things in the MLM world. It's not just latent basis and SEM. There's that whole family of models as well. Yeah, I think we got most of the list. Good. Any questions about any of that? All right, number 3 then. How are fixed and random effects, so fixed effects and random effect variances, more specifically, as we would call them in multi-level models, specified within the SEM world? This can be summarized, I think, in one sentence. What's my sentence?
Mean and variance of latent.
That's it. The fixed effects are latent variable means. The random effect variances are latent variable variances. That's it. That's the translation. So the idea is that when we write out a multi-level model, in the level 1 model, we have what I call placeholders, like the betas that hold the fixed and random effects that come to level 2. The idea is that we literally put the betas into the code as an idea. So we make a factor and we call it the intercept factor, and we make another factor and we call it the time slope factor. How do I know which is which? Since we're not usually estimating factor loadings, how do I know what my factor means? What it represents, let me say it that way. Like, how do I know that I've made an intercept?
If it's coming from the outcome,
Say that again?
from the diagram, if the latent factor is coming from the outcome,
The
it's
latent,
the intercept, and if it's coming from the time variable, you know it's the time slope.
okay, yes. So in MSEM is what you're talking about.
Yes, and
Then
then
the intercept factor is basically the name of your variable in the between model. And the residual variance for it is the name of the variable in the within model. And this time slope factor would be attached to the path from the time box to the outcome box. So we have what's called a path, which we would call a slope, that itself can become a variable. So we have the middle is the fixed effect and the variance around it is the random effect variance. In the SEM single level version, how do I know which is an intercept factor and which is a slope factor? Factor loadings. I set it up that way. So if I constrain all of the loadings to 1, I'm making an intercept. There are other situations in which I would do that besides growth models, by the way. If I want to account for correlations among the residuals of, say, 3 indicators, and all of their correlations are about the same size, I might fit a random intercept factor for that problem. Because then it's basically saying, well, I think all of these residuals are correlated about the same extent, and I'm going to let the variance of that factor represent that correlation. I think I did this in our paper for one of the other validity measures. And at the time, you were like, why is there a random intercept in here? I'm like, don't worry about it, it's fine. So that's what I did.
Now I know.
Yeah, because in that case, I can estimate 1 parameter instead of 3 and introduce a common source of correlation in the same way that an intercept introduces a common source of correlation. If I have a slope factor, how do I know if it's a linear one or a quadratic one or a piecewise one or latent basis or what? The loadings. Yeah, again, like it's my job to say, I set it up to be 0, 1, 2, 3, 4. That means it's a linear shape. Or 0, 1, 4, 9, 16. I'm making a quadratic shape. I can make piecewise, I can make whatever I want. So we set it up that way. But the key connection is that the beta placeholders are in the model. Their means are the fixed effects, their variances are the random effect variances. Okay, you wrote a note to me. Does that make it clearer?
Yes, it does.
That's better?
Yeah.
Okay. Other questions about that or things you want to discuss further?
Yeah, Lisa, I had a question.
Hit me.
So when we're dealing with unbalanced time, and there's people who come into our study at different points and stuff like that, and we don't want to round our occasions.
Mhm.
If the idea is that we are setting the loadings for our time metric,
Mhm.
so why, you just have to say as many loadings as there are like unique time occasions? I don't understand, like in an how you would deal with that in an unbalanced world.
So in unbalanced world, the easiest thing to do is use the multi-level SEM instead, because you just have your time column in the data set and it has whatever people have and that's it. In the single level SEM world, what you end up doing is having as many columns in your data set as you have like conceptually distinct occasions. Like even if people are unbalanced, like you're probably thinking of this as wave 1, wave 2, wave 3. So if you had, say, a 5-wave study, you'd have 5 columns. And in the first column would be the actual occasion that somebody showed up for wave 1. The second column would be the actual distance from wave 1, like to wave 2. And then you would say, hey, M+, take the values in those columns and make them my factor loadings. Fix them to be my factor loadings, but it's fixed at a different individual specific value for each occasion. That's how T-scores works.
Okay, I see.
T-scores is what it's called in M+. The thing that it's called more generally is a definition variable. That's the term that you would look for like in the search manual. Okay. Levon doesn't have it as far as I know. I don't think Stata has it, but I'm not sure. And MX has it, I believe. OpenMX is the more recent version of that. I believe they have definition variables. Okay, any other questions on number 3? All right, last one then. This is another single sentence answer. What's the big difference between a multi-level SEM and a single-level SEM in terms of how you would specify them? And by specify, I mean write the code and then map that code onto what comes out in terms of the output.
Data structure.
Data structure, that's it. Single-level SEM is wide, multi-level SEM is long. So in a wide data set, for instance, if I have 5 waves, I have 5 boxes for every variable because a column is an occasion of one variable. In multi-level, I would have 1 box per column, and it doesn't matter how many occasions there are. Everything else is pretty much the same. It's just, the intercept factor is labeled with the variable's name in multi-level SEM, but it's labeled explicitly as intercept if you want to label it that way in single-level SEM. Otherwise, it's just data structure. Data structure, though, has implications for what types of models are easier one way versus another. So, for instance, if you're interested in what's known as cross-lagged effects, like your x at time 1 predicts your y at time 2, and your y at time 1 predicts your x at time 2, like these sorts of pictures, traditionally single-level SEM is easier for that because you have access to all of the occasions at once. So I could put like time 1 directly predicting time 5 if I feel like it. In multi-level long data, you can't have predictions that go across rows as readily. Like you're only working with what's on the same line. And that's the limitation that the term dynamic SEM, I'm doing air quotes around dynamic, is supposed to fix. They have ways of creating lagged effects and autoregressive effects that link across rows, which is more challenging. Most of those options require Bayesian estimation in M+, though. All right, that's all the questions. So really, that's the difference, is data structure. But that has implications for what is easier or more difficult to test. So, all right, good with that? All right, then I'm shutting that one off. So yes, this is curve of factors. That's what we were looking at. That's where we're heading to eventually. That's where we're heading to. Okay. So then back to the story. If you want to do one of these sorts of models as a project, that would be fine with me, by the way. I know a lot of you are interested in measurement modeling because of your interest in testing or whatnot, so this would be a nice blend of the two worlds together. We have 3 indicators of a latent construct, and I have 4 measurement occasions. Last time we had started making our way through the configurable models, and I wanted to make a correction. So we were discussing if there were extra things in this diagram, and then I realized after class that the constraints are already here according to his labeling systems. So the fact that like this is labeled lambda 1, and this is labeled lambda 1, and this is labeled lambda 1 means that this picture is actually showing the end result of an invariance analysis where everything is constrained to be the same. I'm lazy and I didn't want to redraw it, and so I'm borrowing the picture. So I had crossed out right here, I just added this x a few minutes ago because the factor means are not in the model in the initial version that we have, the configurable variance model. But they do show up by the end of the process. So just a clarification that these lines should not be here because I'm using this picture to represent the first step of configurable invariance, not the end result. There were some questions about that. All right, do we want to go back over the models or pick up where we left off? What are we feeling like?
Let's go over the models again.
Go over, review or re-go over?
We go over.
Because there's a distinction, right? It's level of detail. So somewhere between review and re-go over? Re-go over? Okay. I can live with that. So configurable invariance is the first step of this process. I'm answering the question, is it consistent with are the patterns of means variances and covariances in these outcomes over time consistent with the idea that I have one factor at each occasion? Like, if not, then it makes no sense to go forward. So I have, let's see here, this is wide data. So note, like, use variables, block 1 to 4, digit 1 to 4, pros 1 to 4. The 1 to 4 are occasions. And yes, you can abbreviate lists like this in M+. It understands that it's filling in 2 and 3. So think about time-saving ways to name variables. Like if I had named this, you know, T1 block, T2 block, I can't use this list abbreviation. It has to be the suffix of the variable for this to work. Likewise, M+ has find and replace, and you can make case-sensitive replacements to edit code very quickly if you have a systemized way of naming things. So I recommend that as well. So the configural invariance model, we're using robust maximum likelihood, just in case there's any non-normality here. It's going to correct the fit statistics and standard errors for that. We are defining one factor for each occasion. So I have 4 occasions in the study. I have named them T1 through T4. You can name them whatever you like, up to 8 characters. The stars in M+ represent estimated parameters. The word by is used to define a latent variable. Do you remember which of these stars I actually need and which are just extra me trying to be clear? The first, yes. So the way that I'm identifying my model is what I would call a z-score scaling or a standardized factor, where the factor means are 0 and the factor variances are 1. That means I need to estimate all the loadings and all the intercepts. Well, if I forget the star here, what M+ is going to do for me by default is fix it at 1. And I don't want a loading fixed to 1 and a factor variance fixed to 1 because that's redundant and it's saying that that indicator is perfect. So it's a double constraint. So I need the stars on the first one for sure. Oh, hang on, come back. I don't need them here, but I'm putting them there because I'm putting stars next to everything that's being estimated. All right, and I somehow accidentally fast forwarded like 8 pages. You know. Next thing, things in brackets are either intercepts or means. They're intercepts if they're predicted and they're means if they're not. So I'm estimating intercepts. And these intercepts are the exact same intercept that you learned in your very first stats class or 8th grade algebra. These are expected outcomes when the predictors are 0. Here the factors are the predictors. Indicator residual variances, these are whatever's left over after being predicted by the factor. So it's not the factor. Those are all being estimated. I am adding 6 covariances for the same outcome over time because I have 4 occasions, so all possible pairs. This is a lot of parameters that I could potentially shorten. Like this would be a good spot for a random intercept factor, for instance. So rather than having 6 covariances, I could have a factor that is just for block, that is uncorrelated with all the other factors, and it could create a constant correlation over time among blocks residuals. Or I could let the factor loadings vary, and that would still be 4 factor loadings instead of 6 covariances. So that would be a way to save parameters if I wanted to. Last but not least, the structural model. Factor means are fixed to 0, because the factors, the predictors here. Factor variances are fixed to 1. That's to identify the scale of the model. And I'm letting all possible 6 covariances among the factors be estimated. So there's no constraints whatsoever other than the ones that we need for identification. That means this model should fit well. If this model doesn't fit well, you got to make it fit well. Because everything we do from this point forward is making it worse, taking parameters away. So I added the ones up here. The curved arrows into itself is a way to represent a variance of that variable. Curved arrows between variables represent covariances. Directed paths represent slopes. So this is saying that the factor at the first occasion is predicting this outcome at the first occasion. The slope is the factor loading here. Then we have The stupid triangle thing, which is a way to get the means and intercepts into the diagram, also predicting here, and these are the intercepts for these variables, and this is the factor means for these two, which we don't have in the model yet, but we will. And we only have 3 occasions, which is why the last box is X'd out here. Or 3 indicators, excuse me, 4 occasions. Okay, any questions on that? Cool. And as I told you last time, it fit. Which log likelihood am I? I'm the hoe. Yes, you remember that. Yes, I sent Lindsay a message on Facebook last weekend, thanking her again for having asked that question. Because yes, we are the hoe. So this is my log likelihood. In log likelihood, is bigger better or is smaller better? Bigger better in log likelihood. So -2 log likelihood is not given on this output anywhere. You'd have to -2 it yourself. AIC and BIC are in the -2 format though. It's internally inconsistent, but that's the way they do it. Same thing happens in Stata, which only gives log likelihood by default. Chi-square test of model fit, this is telling me the difference between the best possible saturated model, which is all the means, variances, and covariances directly estimated in my HO model. And the fact that this is non-significant is good news or bad news? That's my p-value, 0.58. Good news. I know. I couldn't believe it. I had never seen this happen in any data that I've analyzed before. It actually fit. So my model is not significantly worse than the best model. I saved 30 parameters, so my latent factors are doing the job of recreating the means, or excuse me, the latent factors are doing the job of recreating the variances and covariances of my indicators, covariances especially, and each outcome has its own intercept, which is perfectly recreating the means. So really where this 30 comes from, because each outcome has its own residual variance, its total variance is going to be recreated just fine. Because each outcome has its own intercept, the means are going to be recreated just fine. So really what this boils down to is, are the covariances among these indicators adequately represented by the latent factor loadings and the covariances between the factors? That's where the savings of degrees of freedom usually comes from. This is warning me that because I'm using MLR, I can't just take the difference between the HO and H1 models times -2. So there's an extra step that involves these numbers right here, the scaling factors. I have a spreadsheet for that goes with this example. RMSEA, CFI, and SRMR are other indices of fit. RMSEA and SRMR are how much worse than saturated. CFI and TLI are how much better than null, and these are the ones that we need to recompute if we're doing a growth curve type of analysis. In this context, it's okay because there's not a growth curve yet. This result we can always ignore. This has nothing to do with our model. And then last time I actually screwed this up. Do you remember that? I got it backwards. So what is the right way, say, to describe this factor loading? It's 10.6. Someone tell me the right way to interpret this. Nobody knows? You know this.
For each standard deviation increase in theta, the predicted outcome increases by 10 point per digit.
Yep. So for
Increases by 10.648.
For every 1 unit difference in the factor, and a unit in this case, because the factor variance is 1, is a standard deviation. The outcome goes up by 10. Yep. Yep, very good. So note these kind of have similar patterns over time, but they are not on the same scale. We've essentially re-standardized the factor at each occasion, so they're not comparable, but they're proportionate. We would expect them to be reasonably of the same pattern. These outcomes are on 3 different scales, so we can't just look at these numbers and know which one is relatively more important. We would need the standardized loadings for that, but we're not going to do those today because that's not part of the invariance focus. Then we got factor covariances. These are actually correlations, given that the factors have standardized variances at this point, so these are pretty high correlations. These are covariances among the residuals, so they're not correlations, obviously. You can't have a correlation of 7. At least it wouldn't go well if you did. Most of these are very significant. Well, most of them look like they would probably be sizable correlations based on the scale of these variables. Means are 0. The intercepts are all estimated. And because all the factor means are 0, these are the indicator means directly. So what is happening to block design scores over time? Softball question. They're decreasing. Yeah, aging is not good for you. Things go down. What's happening to digit span over time? And prose recall, decreasing. So one of the questions we have to answer is, are these three patterns because the latent factor of cognition is decreasing over time, or are these caused by something else in addition to cognition decreasing over time? So that's where we had left off, is the scalar stage, I believe, is where we were just starting, and that will answer that question. Likewise, the loadings. It looks like for block 1, for instance, that the loading is increasing over time. That could be because of a change in what the factor scale wants to be. So the loadings could differ over time because the factor variances differ over time, and what a unit is differing over time. So our question is, are the differences over time in these loadings caused by differences in the factor variance, or are they caused by something else? That's the idea of testing invariance. All right. So the first thing then, after we establish that our model has some decent fit to begin with, is to see if we can make it not worse by adding constraints. So full metric invariance, meaning that I have constrained all 3 loadings. So the labels in here that happen before the semicolon and on the same physical line of code, they have to be, you cannot return, M+ will not allow that. So BL is being applied to all the block loadings, DL is being applied to the digit loadings, and so on. So I've labeled those in the picture. Because I have constrained all the loadings to be equal, the factor variances at the occasions 2, 3, and 4 get free. The factor variance is still fixed to 1 at the first occasion for identification. So now the loadings and factor variances are on the same scale. We saved 6 degrees of freedom by doing that, because we used to have 12 loadings and now we have only 3, but we had to add 3 factor variances back, so it's a net savings of 6. Our model still fits well according to all of these indices, but the test of whether we made it worse is to compare our previous HO, the configural model, to this one. And survey says, if I'm using a traditional alpha of 0.05, yeah, I made it worse. And so this was the point at which I diverge from the authors of the chapter that I assigned for this unit. It looks like it's worse by about 15. To figure out why it's worse, I look at the modification indices with respect to the constraints. So there's like a whole list of things that it wants to tell me to fix the model, but I'm only paying attention to the ones that go with my constraints. And this is telling me in particular that the loading for prose at the 4th occasion wants to be bigger by about 0.3. And if I allowed that change, the chi-square would improve by about 7. So my philosophy is this. The whole change overall was 15, and like half of it is due to 1 loading. To me, that indicates that I should probably let that 1 loading be free. So I did. So here's what we ended up with the solution in terms of the shared factor loadings. Factor variances then show an increase over time, and it's all relative to what the scale of the model is. So these mean that because the factor has a variance of 1 at the first occasion and has a variance of 1.1, 1.2, 1.5, variance is increasing. People are becoming more heterogeneous in their factor scores over time. Okay, here's my partial model. What's different? Yeah, the 4. Yep, so this one's different because it has a different name. That's how I know. And I put it over here in the picture here too. That's the only thing that's different. So now if I compare my new partial metric model back to the configural, it is not worse. So good to go. So this is the idea of partial invariance. It doesn't have to be all or nothing. So what happened is the loading actually is 3.9 and the others are 3.3. So it looks like prose recall is a little bit more important at the fourth occasion. But nothing that would compromise my ability to talk about this factor as cognition. What would compromise my ability to talk about it as cognition would be like if the importance of the loadings changed to where it was like more block design at first, but then it switched to be like prose recall by the end or something. Which loadings are relatively strongest tell us which of these is going to be more indicative of the factor, more related to the factor. And I think that was about where we left off. Did we get to scalar? Did not? Okay. Okay, any questions on that review / re-go over? Okay, scalar then is either intercepts or thresholds, depending on what kind of model you have. The idea here is saying that the only reason why there are changes in the means of the indicators over time is because of changes at the factor level. If so, then I can constrain the intercepts to be the same over time. This is why I always hit the point that it's an intercept and not a mean. The intercept is at a factor score of 0, here's the expected response. The mean can change over time, but the intercept cannot. So I added, note that the constraints go down for the loadings because of the way I wrote the code, but they're all on the same line because I have block 1 through 4. So BI is the intercept for block DI and PI, which that would be putting these constraints on here. And then now the triangle does get to predict the two means of these latent factors. This was the Y-looking path here, but I greened it out just to make it consistent. And the factor means are being estimated at times 2, 3, and 4. Okay, so the logic then is, if it's the same, if it's the factor that's causing mean change, then we allow the factor means to change. The intercept should be able to stay the same. Survey says, saved another 6 degrees of freedom, 12 intercepts versus 3 and 3 factor means. No, it's not worse. Very surprised by this result too. This is like the best real data invariance analysis I've ever seen. That's because I only have 3 indicators, right? Like that's not a coincidence that I narrowed it down to where I wouldn't end up with like scalar J or something in my naming conventions. So yeah, it looks like, here's the relevant part of the output. So now the intercepts are constrained equal. So for a factor score of 0, my predicted outcome in the block design test is 10, regardless of which occasion it is. However, what's happening to my factor? Relative to a mean of 0. Yeah, so this is another, like you have to know what the scale is to know how to interpret these numbers. If the factor mean is 0 at the first occasion, these negative values indicate a decrease. Each of these is being tested against 0 in this Wald test right here. The null hypothesis is 0. So each of these represents a test of whether this factor mean is significantly different than 0, which is significantly different than time 1. All right, next step then, residual variances. Because I only have 3 indicators, I am not kicking prose out of the model with respect to its residual variance. I'm going to try to constrain it anyway. So that's another something different that I do in this context. Normally, if you have an indicator that its loading fails in variance, you would like kick it out from that point forward. Because I only have so few, I'm going to try and keep everything constrained that I possibly can. So I added these constraints to the residual variances, BR, R for residual, which would show up for the pitchfork-looking residual variances in the picture here. There's nothing else I have to do at the factor level. So residual variance doesn't require freeing anything. It just constrains it. And what is a synonym for residual variance invariance? There's another set of terms. starts with an S. Loadings is weak. Scalar is strong, and this is strict. Yes, that's another set of terms people use. I know. My preference is to say, I constrain the intercepts, and then in parentheses, scalar, comma, strict, right? Like, tell them what you constrain. Don't make them learn the names. But the names are used consistently, at least in the world that I live in. We saved 9 degrees of freedom. Is it worse? Wah, wah. Decidedly so. There's 2 culprits according to the modification indices that are responsible for most of it. So I decided just to free both of those at the same time. So note the placement of the semicolons here. So I have BR1 as a label for block 1, a semicolon, and then BR as a label for these. So this is like 2 separate statements with respect to how the constraints are being read. I didn't have to put labels on these first ones, I just did so for completeness. So it looks like block design and digit have different residual variances at the first occasion, the others are all held together. And now it is not worse than the best possible model, still fits pretty well on the whole, and here are the results with respect to all the parameters. So I printed everything at this stage because this is our new baseline. This is what we're trying to model growth in at this point. So note this loading right here, 5.972 is going to show up in the next model. At this point in the solution, the first occasion's factor has a mean of 0 and a variance of 1, and that's what's setting the scale of the model. So a loading of 5.972 for block design is consistent with a factor variance of 1. I'm going to use that in my next analysis so that I don't have to fix the factor variance, but I still basically get something that's sort of standardized. And the loading is 3.9 instead of 3.3. I can live with that. Intercepts are all invariant. Here's the factor means. Here are the, factor means and factor variances. And so I computed the relative change between these to make a point. The change from time 1 to time 2 is negative 0.11. The next change is negative 0.146, and the one after that is negative 0.22. So this tells me that a linear growth factor is not going to fit this pretty well. This is an accelerating pattern of decline. They're going off a cliff, basically. So I'm going to latent basis this instead. Likewise, factor variances are increasing over time. That tells me what about what kind of random effects I'm likely to need. If my variances are changing over time, what is that a symptom of?
Between person variance is not stable.
Yeah, this is a signal that we need. We're going to need a random slope of some kind. If all my variances were basically the same over time, that's an intercept model. So when you see variances changing in a pattern like this, you needed some kind of random change slope. In terms of the residual, it looks like there's more leftover variation in block design and in digit span at the first occasion relative to the others. I don't know what to make of that, and no one cares. Well, because it's not the factor, right? Like I can't, like all I can say is it's whatever is in block design that's not cognition. I don't know what that is. It's not my job to know what that is. So I'm just going to let them be a little bit different. But on the whole, I only had to free 3 things to make this model work. So that's a partial invariance model, but it's still pretty tightly held together. Okay, the finale, latent basis.
I didn't get that. Could you try again?
No, I may not, Siri. She never listens to me when I actually want her to. That's the thing. Yes, sir.
So the idea is that before you even move into modeling growth, you have to establish a model under which your construct is invariant, either partially or fully invariant.
Yes. Before we model growth, we're establishing that our construct is reasonably invariant over time and how it's being measured. So these structural model parameters, the factor variances, the factor means, and all of the factor covariances, that is what our growth model is going to be predicting. So in the same way that our lower order factors were responsible for recreating the covariances among the indicators, my intercept and slope factors are responsible for recreating the covariances among the lower order factors. But in this case, also their means and variances. We're going to push everything up. So this is the answer key with respect to what type of pattern the fixed and random effects are trying to be producing. This is what they're trying to produce. Okay, so I got to change the way that I've identified the model to do this. So first big one right here, I have fixed the factor loading to the first indicator, and I fixed it equal, but I fixed it to what it was in the previous model. So here's the logic. If I had used the old method of identification saying factor variance at time 1 is 1, that could cause estimation problems because that number needs to be movable because it's now going to be predicted by other things. It needs to become factor variance left over, which is called a disturbance variance. So in order for its variance to be split between what the intercept and slope factors are and the leftover part, it has to be an estimated quantity. Rather than fixing the loading to 1, I'm fixing it to 5.972 so that the total variance at the first occasion in the factor is still going to be roughly 1. So I'm keeping the numeric scale the same, I'm just doing it in this sort of roundabout way. And this was discussed in the textbook as well. So because I've fixed the factor loadings for the first indicator at the lower level, I can now estimate all of the factor variances that will become, as I've labeled them here, resvar. So at this point in the story, these circles are like my observed outcomes, whose means and variances and covariances are going to be captured by the higher order factors up here. So we're working with just this part of the model as the new component. Intercepts are still held equal at the lower level. Residual variances are still in this pattern at the lower level. So the new parts here. The lower order factor means are all shut off at 0. The reason I'm doing that is so that the mean change that I saw, that accelerating decline pattern, that's going to go up to the slope factor mean. The slope factor mean is going to be recreating what the factor mean is at each occasion. Likewise, I'm constraining all of the lower order factor variances to be the same with this label resvar because they are going to be essentially my R matrix. So these are my level 1 residual variances now. And I want them all to be the same so that any heterogeneity of variance is up in the slope factor. Likewise, all covariances among the lower order factors are 0. So these two are essentially creating a diagonal R matrix. The level 1 E variance is the same across time with no covariances. That's what I'm doing here. My T1, T2, T3, those are like my observed outcomes in our previous life. Okay, I feel like we're losing the plot a little bit here. Or is that just me? It's just me? We're losing the plot. Okay.
No, yes, I've said yes to we're losing the plot.
Okay, yeah.
It's just.
Well, it could be me too. We could all have lost the plot together. But
What's the forest?
yeah, what's the forest? Okay, hang on. I need a picture. I need a picture here to reacquaint us with the thing. I need a picture. Hang on. I need this picture. So, what if we just had a just typical, not latent, just regular flavor growth model, but I'm doing it in SEM software? Then I would say that the means of my latent factors are the fixed effects. The variances of my latent factor and their covariances are the random effect variances and covariances up in G. The loadings are my Z matrix that is the predictors to be given random effects and their values. And the residual variance of my outcomes is my R matrix right here. Okay? Now pretend that these boxes are my circles called T1, T2, T3, T4. So I'm constraining the variance of my lower order factors to be the same because that's my R matrix that I'm trying to make diagonal with no covariances. These higher order factors up here are going to be responsible for recreating the covariance over time. Remember, the job of random effects, what they're saying is that they are the reason why the outcomes from the same person are related. They are the reason. And once you put them in the model, the outcomes are independent. Right? Most of the time in our R matrix, we don't have any residual covariances. If we wanted to have like a lag1 covariance, we could add like two-headed arrows among the boxes here or something like that, but we don't want all possible covariances. So in this version of the picture, I shut off the covariances among these four so that all of that information goes up here. Likewise, I shut off all the means so that the means of the intercept and slope factors are responsible for introducing mean change. I constrain the variance of these to be equal so that any heterogeneity of variance is being reproduced by the slope factor.
Wait, say that last one.
I constrained the residual variances of these factors equal so that any change in their variance over time is captured by this up here. Remember slopes, when you fit a random slope, it has a quadratic pattern of variance heterogeneity. That's what it's introducing. So what I'm trying to say, forest, not a person, but forest for the trees. What I'm trying to say is that the job of these latent factors here is to reproduce the mean change over time in the lower order factors. That's what the intercept fixed effect and what the slope fixed effect is for. The intercept factor would recreate a constant pattern of correlation among these things, right, with the ones. A non-constant pattern is introduced by adding the slope variance. The random slope introduces heterogeneity of variance and covariance over time that used to be down here.
And it's only to 3 because we had
This one's 0. They just didn't draw it. Yeah, I don't like that either, but we're missing an arrow here that should have a 0 on it. Let me try another way. Let's see, 141. This will be my last thing I say. Yeah, we're gonna re-go over this. Go over it? I think no. This is the first time we've seen this. Okay, let me say it another way. Do you see the green and the yellow? Okay. Saturated means. Okay. Unstructured variances. Unstructured covariances. Okay, this is like my answer key model, but at the level of the circles. And so what I'm trying to do, no, and this is from the previous model here.
Okay.
This is my last invariance model, which is my new baseline. It is conceptually a saturated means unstructured variance model, the answer key for what the fixed and random effects are going to be trying to reproduce. So I'm taking as much of that information and pushing it up through these constraints in the same way that we would in a single level SEM for an observed outcome.
So we basically made our own answer key model.
Yes,
So that when we're looking at the next model, we're not accidentally accounting for things that should already be accounted for. I think I made that one.
yeah, I can't agree with that one. But,
Okay.
but the first half of it, this is our answer key.
Yeah.
These are the patterns that the intercepts and slopes are going to be trying to recreate.
Yeah.
So the question is, are they enough to recreate them? And if they are, then I can constrain all these means to 0, because the slope's in charge of that now. And I can constrain all the residual variances to the same number, because the slope variance is in charge of that now. And the covariances are gone, because the intercept and the slope variances are in charge of that now. Okay, I'm just gonna stop there. That's it. That's it. It's 1:43 anyway. But yeah, we will re-go over this.
Lisa,
Yes.
in page 13,
13.
in the gray box
Yes.
with the new code,
Uh-huh.
I have a question related to the slope by, because there you are using T2 start and T3 start.
Yes.
But in the book chapter, they use specific numbers trying to represent the middle points. So
Yes.
what do you choose these starts to be estimated instead of fix those slopes?
This is a latent basis model. So in a latent basis model, 2 of the loadings have to be nailed down and the rest can be free. So I set the beginning and the end. And the reason that I did it this way is because in the answer key, this does not look linear. So if I fix the slope loadings to 1, 2, 3, 4, that's a linear function. This is an accelerating change. There's a bigger difference as time goes on between each pair of occasions. So I'm trying to let the estimated loadings create a nonlinear change function.
Yeah, that's really in the book chapter 2, because they also have this nonlinear change, but they decided, because they had 3 slopes, they use 0 and 1, and in the middle they use 0.5.
That's a linear change function then.
Okay.
Because, yeah, so if I don't know if I can do the math correct. Yeah, this would be like 0.33, 0.67. Like
Yeah.
if I fix them to numbers, that would be a linear change
And
function.
then okay, thank you.
And the extent to which they deviate from that is an indication of nonlinearity. All right, I'm done talking for real this time. It's Tuesday, which means thanks for being here. See you Thursday. Let me know if you need anything. Office hours are tomorrow as well. And yeah, thanks for hanging in there. We'll get through this. We will.